terms of our Ieee 754. As in our previous video, we did cover Ieee 754, but in terms of the single precision and double precisions, let's do some recap. You can see now under Ieee 750, we can divide it into one is single precision and second is double precision. For single precision, it is a 32 bits, and double precision is double, which is 2 times bigger than single precisions. In that, it is a 64 bits. And now you can see we also already tackled into the general form of the Ieee 754, and the format in terms of single precision you need to remember. Okay, the format you need to remember, especially how many bits for sign. Of course, of sign is always 1 bit, and I also always mentions that if you have a positive number, your bit for your sign will be 0, and for negative going to have a 1. And how many exponent bits for MIPS 32 bit, which is single precisions floating point number? It is total up 8 bits. And after that, you have a fraction, and these are significance, and this a total of 23 bits. And for single precision, double precision, both have their range from smallest fractions to the largest numbers. What is the range that we cover is for single precision 2 past 10 times with 10 to the power of minus 38. That is the smallest fraction numbers can be supported under MIPS 32-bit floating point. And we also call it as a lower bound. While for the largest numbers, or the upper bound that can support, which is 2 times with the 10 to the power of 38. This is called as a single precision or 1 words. And after that, we already discussed on the problem that might occur in our 32-bit floating point or single precision, which is sometimes you're going to have too large for your exponent, and sometimes your negative exponent also is too large. If exponent too large, it's called as a overflow. So you need to remember the scenario also. If negative exponent is too large, it called as underflow. I hope that you know what is the meaning by negative exponent and what is the exponent. Of course, this is a positive exponent. The number is too large, that it is overflow. But if let's say you have negative means smallest exponent. If it is too small, it called as an underflow. So because of this problem that might occur in our single precision format, that's why there is a solution which is come with the double precision floating point. And for double precisions, again, it is a 64 bits. And similar to our single precisions, you need to have what you need to know basically on terms of the format. First, in your sign should be 1 bit, and then your exponent, it's slightly different. With your single precision, if you single precision, either 8 bits. And now for double precision, it is a 32 bits. Don't ask me why it is 11 bits. I call it as a it is 11 bit for exponent. So So don't ask me why it's come like this. This is a format, standard format for double precision. So you need to remember this. And then you have a fraction. For fractions, similar to your single precision is 23 if I'm not mistaken. You need to refer back to the previous slide. It is 23. But for your 64 bits, you're going to see you have fractions 20 and 32 altogether will be 52 bits. It's quite long, right? So when you adding all 52 add with 11 add with 1, you're going to get the total of 64 bits. And same goes to the single precision. You will also have the range that covered in our MIPS 64 bits, which is smallest fraction will be 2 times with 10 to the power of minus 308. And then for the largest numbers, 2 times 10 to the power of 308. So as for this, when you have this range, it's called also a lower bound and upper bound. Now, we're going to move to our next subtopic, which is IEEE 754, still under this IEEE, but in terms of the representation. In your previous video, we did see also this one, which is we look into the normalization for IEEE 754. You're going to see that for IEEE 754 make the leading one bit of normalized binary number implicitly. That's why it's slightly different in terms of your normalization in your previous subtopic, which is you need to have like 0 in front, and then after your ready point you need to have numbers that is non-zero. That is called as normalized. But it's slightly different to the IEEE 754. Going to see for your single precision, it is a 24 bits for fractions. And for double precision, it's going to be 53 bits. Why? Although it's showing here for your fraction, double precision, it is a 52. And for your single precision, it is a 23. But when you see on the normalization, it is 24 and 53. Why? That is the standard for significant equation for normalization IEEE 754. 1 plus fraction will be used for your single precision, and 1 plus fraction for your double precision, you will get 53 bits. Let's take a look into the format. This is the format standard for IEEE standard for normalized floating point. You got here is a -1 with the sign, multiply with 1 plus fraction, multiply with 2 the power of e prime. If you check back, I need time to scroll back. Where is it? Where is it? Where is it? Normalization. Normalization. Slide. Okay. This is our normalization for our normal floating number, which is not the standard for IEEE. And you're going to see for the normalized floating point, you have this equation that you need to follow, which is you have base, you have the e prime or the exponent, you have the fraction, and it lead with a 0 in front. You can see 0 point, your fraction value. but it is totally different with your IEEE. Coming back to the exact slide, where is it? Okay, you can see it's slightly different. You have minus 1 times with 1 here, and then you have plus fraction. Okay, this one is a factorized, so you need to solve this first. And times with 2, 2 is the base, and your E prime. So over here it also mentions like as equal to sign, whether it is a positive for 0 and minus will be a 1. And normalize exponent called as a E prime. Okay, this example I already showed you in your previous video. So you can see if you have numbers 1.03 times 10 to the power of minus 1, you're going to see this is your, not yet, you're going to see this number first. If your number is starting with 1, and after that you're going to see there is a 0, and this will be a, it is not looking at this part, it's going to look into this part which is in front. When it start with 1 and then there is a point, there is any value after that is going to be called as normalized. So this is normalized, and if it's normalized, you're going to know that this is your E prime, your exponent, normalization exponent. For this part, is it normalized for IEEE 754? No. Why? Because it's starting from 0, and this is like your normal normalization, which is not covered at IEEE 754. Then you know that is unnormalized. Later you need to do the normalization. Then you can see also another one. Is it normalized or not? You have 1 in front, and then you have only a single non-zero before radic from this one, a single one non-zero. Let's say you have a 7.2 times with 10 to the power of 16, let's say. So this is non-single numbers before your radic point. Sebelum nombor perpuluhan, before your radic point, it is a non-single. Then it's called as normalized. So please try to look into what is the differentiation between these two standardizations. Now in terms of this table, you can try to do the exercise. Let's say for this part, using normalized binary number and its exponent respectively using a single precision floating point. So single precision is under IEEE. That's why you're going to do the normalization under IEEE 754. You need to move 1, 2, 3. Why you need to go to the 1, 2, 3 to the left? Because after this you're going to see only one single number non-zero before your radic points. If you do like 0.110101, and you're going to be like 10 to the power of 1, 2, 3, 1, 2, 3. So that's why you get here as a exponent normalization, which is your E prime for 3. So this is a normalized form of number, and please try to do all the others example here. For the bias notification, similar to your previous example, you also have the bias in your IEEE 754. It's also sometimes can occur a bias. So what happened? You're going to have two types, which is bias notification for 32 bits, which is a single precision, and also later is 64 bits. Okay, let's say you have example 1.0 base 2 times with 2 my the power of minus 1. So you need to check first, is it this is a normalized number or not? If this normalized, then you know already, okay, this power or the exponent will be the e prime. So now my e prime is minus 1. So you can see that under exponent here, how to make the e prime to be minus 1, can or not. So can you just apply this IEEE 75 single precision using the minus 1 e prime? So you can see over here, you need to apply the similar uh, equation, slightly a similar equation, which is you have a bias value, but the bias value equation is having the minus 1 at the back for your e prime. Let's take a look the equation last time. Where is the equation? Okay. For your bias exponent, for your numbers, you're going to have b equal to 2n minus 1 for the bias value. But now you can see that our bias exponent for IEEE for the bias, where is it? Okay, for the bias value, we're going to get the equation for b equal to 2 to the power of n minus 1, and you add another minus 1 at the back. And this is fixed, F-I-X, fixed, tetap. If for single precision, it's going to have 1 to 7. For double precision, it's going to be 1, 0 to 3. Why? Because you are looking at this end. Similar end you're going to apply, because for single precision, your end will be 8 minus 1. Then you're going to minus 1 again. So for double precision is 11, right? 11 minus 1, and then you have minus 1 again. That's why you will get 1023. Please try to calculate it using your calculator. And the example here, it shows already similar example. And your exponent now, we're going to change into bias exponent. This is our e prime. E prime is our normalized exponent. And how to get EB? This is our bias exponent. EB equal to E prime plus our bias. Now our bias for single precision will be 1 to 4. As I already mentioned, it is a fixed for 32 bits. And now you get E prime as minus 1. That's why you will get 1 to 6. 1 to 6, you convert to the binary, you will get this value. And you put all together in your 8 bits for your bias exponent. But for this part, it doesn't matter because you have already the normalized value. And it's going to apply the similar things. You're going to padding to the right. If let's say for your bias here, you have like 0, you're going to get like 1 1 only. So your answer will be 1, 1, and you're going to padding 0, 0, 0 to your left. Okay, this is your single precision format. This is your double precisions. And you can see you have the bias exponent 8 bits. For double precision, your bias exponent will be 11 bit. This one is 52, this one is 23, similar to your normal single precision and double precision. Only the things that make difference is you need to play around with the value of bias exponent. You cannot simply use the exponent value here because there is a possibility of negative E prime. Okay, try to complete this table with the bias exponent, which is EB, and binary representation. This one, okay, it is not too hard because you know already, as I already mentioned, for single precision it is fixed already. Let's say you have exponent. I give you one example. I forgot. Oh, it's 1 to 6. 1 to 1 to 6 or 1 to 7. 1 to 7. For single precision it's going to be 1 to 7, and you're going to add. See, we're going to add for your E prime, right? This one is EB equal to E prime plus your bias. Your bias is 1 to 7 for your single precision. I put here, okay? 1 to 7, and for your double precision is 1, 0, 2, 3. And the only make difference which is for your E prime. Now your E prime will be 3. That's why you will get your value 130 for your EB. Then you try to convert to binary. What is your answer? For minus 3, you will do 1 to 7 minus 3. Then you will get 1 to 4 for your bias exponent. But for double precision, what happened? You're going to have 1, 0, 2, 3 plus with your exponent E prime. You're going to get 1, 2, 4. 1, 0 to 4. 1, 0 to 6, sorry. And then minus 3. You got 1, 0, 2, 3 minus 3. Your answer will be 1, 0, 2, 0. And try to do the rest. And convert back to the binary. Then you can apply in terms of this floating point format. There is an example after this. Here you can see it shows you step by step how to convert decimal to binary floating point using your IEEE standard. First, you're going to do the normalization. Then you determine the sign of bit, whether it is a positive or negative. Then you determine the bias exponent value. And lastly, the fraction. Very simple 4 step. Okay, now you have example here. 10.4 base 10. Using a single precision floating point. Single precision in your mind is already IEEE standard. So this is not normalized because you have 1, 2. 2 number before your plotting your ready points. That's why you need to move this first to here, so then before your predict point is going to be only one single value with non-zero. Now I'm going to move to my left. I'm going to get 1.04 base 10. And I'm going to multiply with 10 to the power of minus 1. 1 because it's go to the left. Positive 1. So now I have the normalization I knew already my B equal to 127. How about my EB? It's going to be E prime. E prime will be 1 plus with 127. I'm going to get 128. Now, I don't have calculator to convert to binary. Let's take a look how it's going to do. Okay, you can see this one is directly change first to the binary. But in terms of decimal also you can do it. But this is mentioned, this is decimal, you need to change to the binary. So when you change to the binary, you get this value. It doesn't matter, you can change its letter also. You have 0, 1, 0, 1. This is 10.4. But for here, you need to also convert to your binary. You're going to do the repetition multiplication. If you still remember, you're going to have 0.4 multiplied with 2. Why 2? Because you want to convert to 2, which is base 2. Then you will get 0.8. Your 0.8 you will bring down. You get 0.8 times with 2. You will get 1.6. 0.6 you're going to bring down. You're going to multiply with 2 again. You will get 1.2 until you get 0. But if you didn't meet with 0 at the back, what you're going to do, you're going to stop it for decimal floating point, or depend on the question. Sometimes it's like giving you three floating point and etc. So it's depend on the question. Okay, now, okay, this is the one that I shows you. Conversations are converting from your 10 base to your binary. You get this part, and when you do the repetition multiplication, you will get this. Of course, going to like continuous, but going to stop at the 4 decimal floating point. So 4 times only. And what is your answer? Your answer will be 0, 1, 1, 0, and you put the radix from in front and you combine it together. When you have this one, you're going to get 1010.0110. If this case, what you're going to do is you're going to normalize it first. 1, 2, 3. 3 times you're going to get 0.0100110, and this is the normalized, and you're going to times with 2 the power of 3. Then the normalization, it's easy for you in terms of E prime. You already get the E prime. So let's take a look in the proper way. The similar things that I got just now. And determine the sign bit. Sign bit, of course, you can see it is a positive number. You're going to get a 0 in front. See? And next, determine the EP. EB, our B, which is bias, already fixed, as I mentioned, 1 to 7. No need to add it. Our E prime, we already get it as a 3 here. So we just apply, that's why we get 130. Similar things, you convert it into the binary. This one I also get just now, right? So you convert to your binary. You got 1, 2, 3, 4, 5, 6, 7, 8. 8 bits already. So it's full house, and you can put into your EB place. This is one sign, 1 bit, and then you have 8 bits. 8 bits. And after this, you're going to have 23 bits for your fraction. So this will be putting here, your sign will be 0 and 23. This is the value you put here and you going to padding to your right, 0, 0, 0, 0, 0 until 23. So my drawing is very ugly, you can see in a proper way here. So you need to determine the fraction. You have EB 1, 0, 0, 0, 1, 0, 0, 1, 0. So this is your value for your EB. And for this part, you're going to see after you get the EB, you need to apply into the EB section. But before that, it shows you also on the fraction number. So what happened to your fraction number just now? Okay, this is your fraction number. Where is it? Okay, this part, right? Okay, this is your fraction number. And you're going to padding to the right. This is okay. This is your fraction number. Now what happened is you just put it here, and this value you put here, simulating with that I done just now, and the sign here, and you padding to the right, 23 bits. It's very easy, right? Now you also have another example. Let me show you this one example. After this, you have another one, two. Try to do by yourself. Okay, here I have negative number. My sign will be 1. And I got 0.75. Alamak, how to do it? Then 75 over here. This is our fraction number. We're going to do the repetition multiplication. We have 0.75 multiplied with 2. What we'll get? I need to check my calculator. 0.75 times 2, I get 1.5 here. And I will bring my 0.5. I'm going to times with 2. Oh, I got already 1.0 only. Then I will directly stop, because if I bring 0 in front, 0 times with 2, of course I'm going to get 0. So it's no need for you to repeat if you get a 0. What is my answer? My answer will be 0.11. Why? Because this is my value of the answer. Now this is my number for 0.75 decimal. I convert it into binary. I get 0.11. After I done this is not normalized number. What will happen? I'm going to normalize it. This one is multiply with 2 the power of 0. I'm going to move to the right because I need one number at least before my random points. I'm going to get 1.1 multiply with 2 the power of negative 1. 1 negative 1 because I move one time to my right. After that, we're done with normalizations. We can easily get the answer. Now, I have one here. Oops. What happened? Okay. I have 1 here, and I have my floating point as a 1. Also 0.1. How to do it? This is my negative 1 E prime. My B will be 1 to 7. And my EB will be 1 to 7 minus 1. I get 1 to 6. Please convert this to binary and put it here. My sign here will be 1 because this is negative number. And how about my significant or fraction number? This will be putting everything here, which is 0.1. You can see 1 0 0 0 0 0 until the rest. Similar to what happened here also. Okay, try to do the exercise number A and B. Or you have many exercise. It's better for you to try all. It is similar step, so it is not too hard for you to do so. Now, before this, you have conversions decimal to binary floating point. Now, if you have the binary floating point, you need to change to decimal. So it is just a vice versa. To convert a single or double precision floating point to decimal number. Just now you have all in terms of your binary. So in this subtopic, we want to look into our decimal. Let me check. Okay, maybe it's better for me to stop. I'm going to make it to another video, so then it's easy for you to separate which part for this video, which part for this video. Okay. For subtopic under binary to decimal, we will continue with another next video. Okay, thank you.